so we need to move on to the next speaker, which is Sriram Ramaswamy.
Hi, thanks very much for asking me to speak in this meeting. It's not exactly my area of specialty, but it's got a bit of active particles in it, so let's hope for the best. I'll be telling you about work done with Rahul Chhajwa, who was a student in ICTS and is now at Stanford, and Rama Govindarajan, who is at ICTS. And so let me start. So I mean, the talk is concerned largely with caustics, which are these sort of foci or imperfect foci. They're a kind of singular structure that you see all over the place. You see it in reflections on water. You see it in suspensions where flow fields make particles aggregate. You see it in cosmology and so forth. And the talk won't be concerned with the very sophisticated aspects of caustics. You know, really, I don't think Michael Berry would find a lot to pay attention to in this talk, but it is nonetheless about caustics. Okay, so I mean, just to remind this audience, remind myself, you know, in optics, you know that a focus, a real focus for things focused to a point, is something you have to do all kinds of work to ensure it happens, and it's not natural. Generically, the least disturbance, the least aberration, as it's called in optics, disrupts it, and you get pictures like the picture on the right. But even in the picture on the right, there is an accumulation, which is that in general, if you project the light onto a screen, rather than a point, there'll be a line. And if you look at the matter in 3 dimensions, rather than a line, there'll be a surface. So the caustic basically is the envelope of the focused or reflected beam. There's an accumulation of rays tangent to the caustic. And so at that point in the geometrical optics limit, the intensity diverges. Caustics have been discussed a lot lately in suspensions. Wilkinson and Mehlig, I believe Mehlig is in the room virtually, give a very simple and helpful example that tells you what it is. Imagine a 1+1 dimensional phase space, and imagine that this red line, you can see my pointer, right? My cursor.
Yes, we see it.
Yeah. So imagine that this red curve is where the particles are initially distributed in phase space. So then what that means is these particles have a momentum, a velocity to the right. That means the particles to the left of this point are moving to the right, and the ones farther away are moving faster. The particles to the right of this point are moving to the left, and those farther away are doing so faster. So this initial distribution will evolve in this manner. So for example, at some point, it will take this form in which the curve describing the distribution will be tangent to the vertical. So at this point, let us say you focus here. At this point, the distribution in xp space looks like a delta of x minus p squared, roughly, if you think of that as the origin. If you shift your p equals 0 to be here, just my convenience. Therefore, the real space distribution rho, which is the integral of this guy over p, will then acquire a 1 over root x singularity, which is illustrated here at these 2 points, x1 and x2. So basically, fast movers initially behind catch up. In effect, movers with different speeds from different x arrive together, and you get a divergence of the local density. So, and when you do that, you really can't ask about the velocity field of the particulate phase in any meaningful sense, because all the particles have all kinds of wildly different velocities at that point. And this sort of accumulation of particles is what we're interested in this work. Oh dear, it's doing this again. Just a moment. Just a second, sorry. Yeah, I don't know why it did that, but okay. Just a moment, sorry. Where's it gone? Sorry, I think I have to unshare and start sharing again. Can I do that? No. Okay, great. Sorry, hang on. There's something weird going on here, which is not going away. Oops. Can the person in charge remove me from sharing? Will that work?
We can still see you.
Yeah, no, can one of you unshare me? Maybe that'll, because I'm not even able to unshare.
So,
thanks, Klaus. Hang on, let me try again.
Was not to me. Was not me.
Well, I saw your face, so thank you.
Yeah. Anyway, we still see your presence. Now it's gone.
Yeah, no, I'll come back. Yeah, so we'll skip that particular one. So what I'll do is I'll just show you that one without showing you the movie. Yeah, hang on. So yeah, so I mean, you can see my non-presentation screen, right?
yes.
Yeah.
Yes.
Okay. So I mean, similarly, if you have a bunch of particles in a turbulent flow, then even if the flow is solenoidal, so it doesn't actually have a potential part, it doesn't actually converge at any point, inertial particles in such a flow cluster. And this is the kind of phenomenon we're interested in. Let me now go to, yeah. So we care about caustics and objects like caustics where the density gets high because they promote encounters. So in interacting particle systems, with their living organisms or something else, we're interested in aggregation patterns, maybe communication, maybe reproduction, and so forth. So the case we decided, a case for comparison is caustics in a very simple, in 2D turbulence, which is the work of Ramanuju, Perlekar, and Govindarajan recently. If you look at the flow fields of 2D turbulence, it's full of these Gaussian vortices called Lamossian vortices. And they studied the inertial particle dynamics around one such vortex. So Lamossian vortex, for those of you who don't know, has a Gaussian vorticity profile and a velocity field which far from the core looks like the standard point vortex velocity field. And this parameter gamma is the strength of the vortex. This width is the square root of 4 nu t, where nu is the kinematic viscosity. So you can look at inertial particles by way of background around one single vortex of this type. And you can look at them in the simplest form of the famous Maxey-Riley equation, in which there is a relaxation time scale, which is mass over damping, which sets the time over which the particle adjusts to the velocity of the ambient flow. And what you find is that if you have such a vortex, if the particle is released from far enough inside, then you do get a vortex formation. And if this release point R0 is increased, there is a threshold beyond which the time to form a caustic diverges, at which the time diverges. So basically, the particles have to start from far enough inside. And let's say you have 2 rings of particles, one at one small radius, another slightly bigger, and they release, the inner ring will crash into the outer ring, as it were. This caustic formation was discussed in the context of raindrops by these people. Okay. Now, it has recently been suggested that self-propulsion without true inertia can, in a fluid, can display behavior similar to inertial particles. Sokolov and Aronson, for instance, pointed out that you can have particles being centrifuged out of a region because the orientation, which determines the direction of their autonomous velocity, can then be made to point outward, and you can get an effective inertial effect in that sense. So these kinds of ideas and others prompted us to look at the problem of active particles in vortical flows. And for those of you who don't know what active particles are powered or motorized particles, living organisms or some of the energy-using components or artificial self-propelled objects. The point basically is that each such particle has detailed balance broken at the level of that particle. They have fuel, which they turn into movement. If you studied collections of these particles, you'd be studying active matter. But here we'll study a sort of small sprinkling of such particles, not constituting a bulk chunk of active matter, but a dilute suspension thereof. Okay. You can have various kinds of active particles. To be active doesn't necessarily mean that you have a self-propelling velocity, just that you break detailed balance in some way. But the sort of the most obvious kind of active particle would be an object with a well-defined head and a tail, and which is both dynamically and structurally polar. But you can imagine other kinds of cases. You could imagine a particle which has an orientation, but doesn't care about head and tail. Or you could imagine a particle which has a well-defined propulsion direction, but is structurally and sterically apolar. So that would mean if you had collections of such particles, their packing wouldn't particularly care about head versus tail. And if you put them in an ambient flow, unless they had some other kind of effect on the flow, let's say through polar stresses, their orientation would respond to a flow in a manner like an apolar rod. I'm sorry, I'm in an office where the phone is ringing. I guess it's okay. Sorry, talk. Yeah. You can also have active particles that are very transiently self-propelled, but are basically little spherical objects. You might be tempted to call them scalar active matter, like these chemically propelled droplets from Shashi Tuttupalli's lab. What I want to do is I want to look, based on these examples, I want to look initially at a very simple kind of active particle. The idea is the following. You've got a particle whose position is x. It has no inertia. In principle, it's sitting in an external force field coming from the gradient of some potential. It's also sitting in an ambient hydrodynamic velocity field. It possesses a little vector, w. Okay, each particle, this particle is endowed with a position and a little vector w. That w isn't a unit vector or a fixed length vector, but it's a vector which has a transitory existence unless you agitate it with noise. So you could imagine a kind of dimer connected by a spring of zero length at equilibrium. If you give it some noise, it stretches apart. If the head and the tail of the dimer are distinct objects, it's got a polarity which we'll call w. That polarity has a direction and a magnitude. Now, to the extent that it's an extended object, it can do a few things. One is, of course, again, we ignore its inertia as well. So it has that extension variable has a dynamics which is relaxing to zero extension in a time scale tau if nothing else happens. It is in principle agitated by a noise which stretches or squeezes it. But because when it's extended, it can respond to flow, you have a coupling of this form. Okay, S and A are the symmetric and antisymmetric parts of the velocity gradient. This is a standard apolar flow coupling, and this is a polar flow coupling. So what it says really is that if locally you have a velocity field with a curvature, that can sort of pull this guy out a bit. Okay. This problem without flow and without an external flow field, force field, would be x dot is w, and w dot is minus w over tau plus a white noise. So that means that the variable x is driven by a colored noise. In the absence of these other features, the variable x is driven by a colored noise with a single relaxation time. Okay, so x is an Ornstein-Uhlenbeck process. So these particles have been named active Ornstein-Uhlenbeck particles or AOUPs. So we're augmenting that really for the purposes of this talk, primarily by a flow field. We will not worry about interactions with a potential force field. Okay, and that flow field, the kind of flow field you look at, is basically a vortical flow field. Okay, in essence, these self-propelled spherical droplets are kind of like active Einstein-Uhlenbeck particles. Imagine you've got the surfactant, the droplet coated with some surfactant, which transiently, locally, let us say, has less of it here, or has a less effective surfactant here. This imbalance can disappear and the object can once again become completely isotropic. So in that sense, it's like an object which possesses a vector which can in principle change its direction, but whose magnitude itself can go to 0. So this is not a bad candidate for an active Einstein-Uhlenbeck particle. If processes create this kind of imbalance in the surfactant field, they generate a flow and this object can propel. So if this object can go on providing this kind of process on its surface, it can keep propelling. So these active droplets are kind of like active OUPs, I would say. Okay, so now let's look at what will happen. Let's look at these terms once again. The active OUP with flow, as I said, this term is the motility term. It has a coefficient beta. This is the apolar flow coupling. This is the polar flow coupling. In this work, we will not consider the particles themselves as endowed with any kind of active stresses. So we're ignoring the effect of particles back on the flow, which is probably okay if the stresses generated by the particle, by the ambient flow are large compared to the intrinsic scale of stress on the particle. Okay. And what I'd like to argue is that these particles behave an awful lot like inertial particles. So what we can do formally, although we won't use this very complicated formulation of the problem, supposing you take this equation of motion and say, look, what this equation is really saying is that x dot is an object called v. I know how to calculate the time derivative of v because I know how to differentiate each of these guys that constitute v. By hand, I can differentiate, right? So I can build an equation of motion for v dot, and I can finally come up with a pair of dynamical equations. X dot equals v, and v dot equals what looks like kind of hideous mess, but in fact is a lot like the sort of Maxi-Reilly in its full glory, not the minimal Maxi-Reilly that I showed you a few minutes ago. So just to underline that, if you take v, differentiate it, and re-express the rates of change of w in terms of w and u, and then go back here and re-express w in terms of v and the external force field and the flow field, you get a closed set of equations for x and v, in which the only objects that enter on the right-hand side are not the dimer extension vector w, but the actual velocity of the particle. Okay, and in particular, if I carefully write the equation in a form where the object that appears on the right-hand side is 1 times the force plus corrections, then this coefficient tau over mu, the lifetime, the lifetime of the extended state of the dimer divided by the mobility of the dimer, of the particle, sorry, actually enters exactly where a mass would enter in this dynamical equation. So you can actually compare this to the Maxi-Reilly equation for a particle in a flow. So let me reiterate that. This is the equation for our particle. It's got all kinds of things. It's got the force, but it's got all this weird stuff that modifies the force. And the reason for that is that this comes from the fact that the object carrying the motility is an orientation vector. And so you get these flow coupling terms. You get a term that looks like, kind of like a Faxane term in the Maxi-Reilly equation. You get the fluid acceleration and you get noise. So apart from the added mass and the history term, which we won't talk about in this talk at all, you get all the other terms of Maxi-Reilly in some form, and you can track back and see exactly where they came from. So we won't use this complicated formulation. We'll go back to writing our equation of motion in terms of x and w. But it's nice to know that our sort of reason for suspecting that the problem might have an inertial particle like form was justified. So let's see, hang on a second. I also wanted to point out another thing. If you go back to this problem and switch off all the flow and consider the case where the force field is strictly a linear function of x, then it turns out that the whole problem, if you treat v as, as a dynamically variable velocity, then this problem without a noise, without an additive noise in the x equation, but with the noise in the w equation, maps exactly to an equilibrium phase space problem involving x and v, as has been remarked in work by Cates and company, and as also we point out in this paper a few years ago. Okay, so there are visible similarities between the dynamical equations for our active particles and flow. I'm still, as I said, talking active particles and inertial particles in a flow. I reiterate, I'm still talking about a kind of rather weak kind of active particle whose motility depends on its possessing an extension, but that extension wants to relax to zero unless you agitate it with noise or with some kind of extensional flow on it. Okay, but let's see what it does. Let's switch off the noise. The motility is then only transient, and let's put it in a point vortex flow field. If you non-dimensionalize by the relaxation time of the dimer and by a length scale that comes from the circulation of the point vortex and the relaxation time, then you get an equation of motion that looks, rather a lot like a particle with inertia with a centrifugal term and something looking an awful lot like a Coriolis term. So the coupled dynamics of R and L, which is R squared theta dot, where R and theta are circular polar coordinates in this plane, have this form. And then you can ask, what does this object do in this flow field? Okay. And one weird fact about this case is when you switch off the polar flow coupling and you don't have noise, that coefficient that defines the degree to which W makes the particle motile ends up sort of vanishing from the analysis. Not that that term vanishes, but the rescaling absorbs it. I guess maybe in retrospect it's not that surprising, but it looks a bit peculiar to me. And so, as I said, you get these centrifugal and Coriolis terms. The fact that it's in a vortical flow field has been built in to this non-dimensionalization by root gamma tau. And then you can just solve the equations of motion. But first you can watch what it does. As I said, you can see that there's a dense buildup of particles at this radius. So a comparison between active OUP and inertial particles, gives you a morphology that is not that dissimilar. Okay, so if you now solve the equations of motion averaging over the initial orientation, it's a bit like averaging over the initial, give it an initial extension and average over the initial orientation of the extension, then you end up getting a number density with a nice cusp at a certain radius, and you can calculate the position as a function of time, the radius is a function of time, and for different initial conditions which are on this axis, you see paths that go like that, like that, like that, and then you see this sort of accumulation, this envelope of the accumulated paths here. So it's a kind of caustic. Never mind the reference to optical. The point is, it's a kind of, you get this characteristic accumulation, which one thinks of as a caustic. You can, in these rescaled units, if you look at R much smaller than 1, you can do an inner solution. You can look at which two terms have dominant balance, and I think it will turn out to be L dot and R dot over R. You can solve that thus for the velocity of the particle, and in fact, that inner solution actually agrees, gives an envelope which agrees. I mean, the envelope that we saw in a couple of slides ago agrees with that inner solution. I'm feeling I'm going a little fast. Okay, anyway. Beyond the critical initial radius, you don't get caustics. So the crossing time of two nearby trajectories, if they start out too far out already, that crossing time gets bigger and bigger. And as you go to larger and larger initial R in units of the sky itself, you find a critical R beyond which you don't get caustics. You can also plot that against the flow coupling, and you get somewhat odd curve whose this feature, I don't have a very good story to explain exactly why it happens, but this is new enough work that I haven't wrapped my head around it. But you see basically that the threshold R depends on the flow coupling. This is the apolar flow coupling. For low enough values, you get caustics. For large enough values, you don't. Sorry. For a given value of alpha, you get the radius beyond which you get no caustics increases. So the larger alpha is, the more prone the system is to have caustics. You can also solve a sort of a more natural self-propelled particle, which is a particle whose dimer extension has a strongly preferred magnitude. So W again is not a unit vector. So this is, I'm not trying to project on W. This is just W dot is W minus W squared times W. So this is like, comes from a potential with a negative W squared and a positive W force. And this is the flow coupling. And here I've left out the polar flow coupling. If I introduce a noise here, that becomes the active Brownian particle. Normally one writes an active Brownian particle with a strict fixed length, but that's really immaterial. This is a softly fixed length. And x dot is flow field plus motility. We'll call that the velocity. That object also displays a caustic formation. The difference between the ABP and the AUUP is that these particles keep moving because they have a preferred extension, and if they have a non-zero preferred extension, they have a non-zero self-propelling velocity. So they'll keep going outside this region. But the point is, nonetheless, you get this caustic formation. So here also you get an effective inertial dynamics. You can put these types of particles in turbulent flow fields and then solve the problem, solve for the flow field numerically and evolve the particle along with it. At low activity, you get some accumulation of particles. At intermediate activity, you get a strong accumulation of particles. We'll come to where you're getting the accumulation of particles in a moment. And at very high activity, again, you get only a modest accumulation of particles. You can ask what's happening here. In fact, what you're seeing here is these are the vortical regions and these are the straining regions. At these intermediate parameter values, if you measure the distribution of the Okubo-Weiss parameter, which is vorticity squared minus strain rate squared, you can see there's a strong tendency at intermediate activity for the particles to accumulate in regions of negative Okubo-Weiss, okay, which again is similar to the kind of thing that happens in for inertial particles in turbulence. Yeah, as I feared, I finished way too soon. Strong clustering and straining regions for intermediate activity. Okay, so yeah, I'm afraid I've talked too fast or I said too little. But anyway, so the summary is that in flow, active non-inertial particles resemble passive inertial particles. Caustics emerge naturally in these active Stokesian suspensions in vortical flow. They're more pronounced at a sort of sweet spot level of activity. We haven't really looked at the competition of these effects with self-propelling stresses that the particles carry, or looked at how particles with such active stresses interact in flow fields, and we haven't really looked at the role of noise. Those are matters that we will look at. But for now, that's the burden of my song. So I can take questions, which is fine, and I could also tell you a completely different story, also about aggregation induced by active flow. So it's up to you.
So thank you for the presentation. So I think it's good if we take the questions first, and then if there's time over, you can discuss some other topics.
Sure. Shall I stop sharing?
You can continue sharing if you want to show something when answering the questions. So I think Filippo was first.
Okay.
With the question.
Yeah, thanks for a nice talk. What I'm not familiar with what you call the polar interaction term. What does that come from? The
okay, so I wish ideally I'd like to draw a cartoon, but let me just wave my hands. For that, let me unshare. Okay. The idea is the following. So supposing, hold on, I'll take a polar object and show you. So supposing I have, actually I need two polar objects. Give me a minute. So first, supposing I just have a shear flow locally, a uniform shear flow, and I have, let us say, a rod. Then, roughly speaking, it'll hang about a lot more along the extensional axis of the flow, right? Okay. Now, supposing I have a flow with a curvature. So, supposing I have a local quasi flow, I can think of that as a patch of one linear shear flow here and one linear shear flow here, roughly. So, let us say it's which way? If I want it to be curved this way, then yeah, so I'm shearing like this. So this guy will align like this in this half. In this half, it will align like this. So now I have these two particles. They could align like this. Now, but where two ends, each particle has a head and a tail, which is different. So you can imagine, several possibilities. But if both of them, let us say, have fat heads, then if the flow makes them sit like this, then they're going to actually not like it. They're more likely to sit with their skinny ends near each other.
Okay.
Right? It's just first, this is one possible way of legalizing that. And if these particles are motile, remember that, right? Then what will happen is this region now has a curvature. And so these guys will actually align preferentially this way, which means the curvature is proving to be an aligning field for the vector order parameter, whereas a strain rate is like an aligning field for an apolar or uniaxial tensor order parameter. Curvature acts like an aligning field for a vector order parameter. And in fact, if these guys are motile, then a curvature will produce a velocity of these particles will drive the self-propelling velocity in a certain direction as well. So that's the story.
Okay, thanks.
So do we have more questions?
Yes, I could maybe.
Yeah, hi.
Yes, Bernard, go ahead.
Oh, okay, right. Well, thanks for your talk. You hinted at the relation between inertial particles and the swimmers. And the reason that there's a similarity is, of course, that they both detach from the flow. Now, when we looked at the inertial particles, we found that the formation of caustics is an escape process. There's a variable that escapes infinity, much like the reaction coordinate in Kramer's.
I see.
Yeah, and for the inertial particles, it's the particle elements of the particle velocity gradient that go to that diverge. So question is, what is it in your case? Now, Kristian and I, we looked at caustics for active particles, swimmers, some time ago. And these were different, but gyrotactic ones. And there we found that the caustics were divergences of the gradient of the orientation vector. Now, how is it in your case?
So the point is, you actually had a field of active particles. You had an orientation.
Yes.
Yes. The problem here really is that at the moment we've really been looking at just the particles as point particles with an orientation. but not with any particular interaction that tends to make the orientations align other than an external field. So there isn't, and then much of what I showed you was averaging over orientations also. Much of the evolution I showed you. So it would be, in your case, your particles actually had steric interactions and tended to align each other also? No. Okay. They were all independent as far as their...
Yeah.
Okay.
It's just a standard model that Massimo and colleagues studied, the gyrotactic.
I see.
And actually, what's quite so the caustics form. How the caustics form, it depends on this gyrotactic parameter.
Right.
And if you take it to infinity, then that mechanism doesn't matter, and the mechanism of caustic formation changes.
I see.
Yeah, and it could be nice to compare it.
Okay, so this is what this is something I will not be able to cook up an answer to off the bat. By the way, we can't see you.
Sorry, I'm sorry.
Really? Okay. Yeah, that's great. Yeah, we can we have this.
It's
that's better. Yeah, it's okay. We can look up to you. But so I'd like to think about those questions. I don't think I have an answer to your question right now. I'll look hard at what you guys have done. We'll look hard at what you guys have done and think about it. I'm not able to make up a story about it on the spot.
And then another question is: Have you considered what all of this means for the encounter rates?
Yeah, so those are the things we're really looking at currently. So at the moment, really, it's I've never given a talk on this before, by the way. It's that new. Yeah, so we are looking at these things. Yeah, because really the interest really is in the encounters. Exactly.
Yeah, and what you describe, it could enhance the encounter rate.
Yeah, that's the idea. Yeah. Yes. So yeah.
And exactly. another question, Kristian, maybe somebody else has a question.
Yeah, so Dhruv asked a question, so maybe you can make an...
I can wait, no problem.
No, Dhruv, go ahead.
No worries.
I've lowered my hand.
Okay, so Dhruv, go ahead and then...
Sriram, quickly.
Hi, Dhruv.
Hi, maybe you can't see me either.
Yeah, I can't see you. Hello. Yes, now I can see you. Yes.
Just quickly, how exactly are you defining the caustics numerically?
So numerically, really if you look at the position versus time for a variety of initial conditions, there's a place where all the trajectories accumulate, at least are tangent to different parts of it, right? So if
so at the end, essentially through the gradients.
Sorry, very crudely, all that we really need to look at is the density, is where the density builds up, right? That's good enough. As far as the object we're really interested in is concerned, it's just where the density builds up. But in fact, if you look at the trajectories, if you just look at R versus T in this vortical flow, what you find is that for some initial conditions, if the initial R is large, they just go off. But below a certain R, they all kiss this one envelope line. Okay?
I see what you...
Okay, so that is what we call the...
Usually you define it through the gradients of the velocity gradient. The
so if you take the particle phase, and define a velocity field for it, there'll be a place where that velocity field sort of has a singular gradient.
Right.
So you can do that, but we're doing it particle by particle, just looking where they accumulate. If you try, so that's right. So I think that it's consistent with it.
Thanks.
Yeah.
Okay. So Massimo has a question.
Yes, just to adapt to what Dhruv and Bernardo were saying. So I think you may try to just work out the equation for the difference in velocity between two close particles.
Right. Yeah.
And that would allow
Yes. Oh, by the way, hi. I haven't met you. I haven't seen you before, I think, Massimo. Nice to see you.
Yeah, so those were good points, Massimo and Dhruva. For the inertial particles, there's a relation between the local collapse of volumes in configuration space, which is this trajectory picture you described, and the divergence of the particle velocity gradient. Just two different ways of looking at the same picture. And so what Dhruva, I suppose, was saying was that now you looked at how the small volume elements collapse. Now you go to your equation of motion and you can figure out what divergence. That could be nice.
Sort of where it ceases to be a sensible field in some sense.
Yeah, exactly.
Yeah.
Oh, and that's another question. Yeah. So if you put your particles in a turbulent field, I suppose there will be fractal clustering.
Yeah. So
yes,
we have. I think so, but we have not measured it.
Yeah, and then it's quite interesting that that this picture of the caustics is a bit oversimplified, because in fact what folds is not a smooth manifold, but a
singular measure itself.
And so now the question is, we've talked about this analogy with Michael Berry's caustic for a long time, but for the light, it's a smooth manifold that folds. Yeah. But in our case, it's a fractal that folds. Okay, so what difference does that make?
Gosh, okay.
That's something.
That's fantastic. Yeah, Thank you. I mean,
yeah, I just wanted to bring it up. I mean,
that's very interesting, very stimulating.
Okay, any more questions or comments? So, okay, so thank you very much.
Thanks very much for indulging me.